we ready? Yeah. Ladies and gentlemen, it's really an utmost pleasure to host Professor Kip Thorne, and I'd like to thank all of you for coming, and especially Jiří Bičák for arranging this wonderful, I hope, will be wonderful lecture. And I'd like to ask Jiří Bičák to introduce our guest.
Well, thank you very much. It's our great pleasure. I apologize to those who were already yesterday in rectorate that some of the jokes will be the same as yesterday. So, but not all. I hope I will recall some other things as well, which I didn't succeed to say yesterday. I will not speak about Bolzano today. Certainly, it's a great pleasure to have here Kip. It's a great pleasure because he has big merits for us, for Czech physics. He has big merits for Karel Kuchař, who unfortunately escaped after Russians invaded, but it was Kip who was arranging his well line in the United States through Princeton with John Wheeler, then to Utah, from which country he comes, and then arranging the letter which was signed by Carl Anderson, whom I probably never met, but Nobel Prize winner for discovering positron, and inviting me to his group, where unfortunately I could come only for a few months, but eventually after the whole Kafkian year I did. And so we are all grateful to him. Now, as I said yesterday, Kip comes from Utah, and where they are very careful about all family trees. And so that was the joke which I repeated, but not everybody was there yesterday. This is Kip Thorne's grandfather. And that it is really grandfather is not only a joke. First of all, this picture is from Caltech, where Einstein was really fighting with gravity on the bicycle. But the second is that it was John Wheeler, the supervisor and mentor of Kip Thorne, who started to do real physical relativity in Princeton after Einstein. And if you remember, I'm now speaking about myself, but a long time ago appeared an interview with Wheeler where he recalls how he was taking classes of students to Einstein house and discussed physics with him. So there was certainly big influence of Einstein's presence in Princeton on John Wheeler, who started, as you know, as nuclear physicist and a very close collaborator to Niels Bohr and involved in nuclear physics, nuclear weapons also, etc., which was also later, who, however, in the 50s started to make big renaissance of general relativity. And actually one can say that Kip is a continuation of John Wheeler without any doubts, and he is continuation of Einstein in the sense that he made relativity, general relativity, which we mostly know as theoretical, beautiful framework and beautiful construction, really physical, and the instrument which was used very much in astrophysics. Kip, as I said, was born actually in Utah in Logan, but then very soon he came to Caltech, and he became one of the first professors in the age of 30 at Caltech. But in between, he had these 2 or 3 years with John Wheeler in Princeton, where already they wrote a book about gravitational collapse and gravitational theory. I just wondered, you were first professor, probably, Feynman professor of theoretical physics at Caltech, not?
Yes, I was the first.
Because Feynman died in '88 and you became in '91. So today, Kip is professor emeritus. And he, as we heard yesterday, so he pushed forward very much all gravitational radiation research, but he produced a number of other things. And so, first of all, they produced this big book, which we know all as MTW, Gravitation, but not all of you know that they published with Blandford. Thorne and Blandford are authors of the book Modern Classical Physics, which again, perhaps even you don't remember, has about 1,556 pages. I don't know, I noticed really it's published by Princeton University Press. There is also some relativity about plasma physics, hydrodynamics, etc. I think book which could be extremely useful for many our students. Kip pushed forward these gravitational waves, both experimentalists and mainly as theoreticians, but also numerical relativists, as he spoke yesterday about it. He wrote fundamental papers I didn't mention yesterday. I was enormously admiring your papers in the use of modern physics in 1980 with all the details about multiple moments, and when he himself did a lot of calculations, but also there was paper with Caves and other about quantum non-demolition about he spoke yesterday. And this is where he is. He retired from Caltech and is now writing other books and primarily also working for films. As you know, he was the main science advisor and production leader or whatever of Interstellar. I unfortunately forgot now at home my bag where I had citations of Kip, what one should do to Nolan, who did the film Interstellar. But the sense was we should always keep physics right, and if not right, so agree on something which all physicists would also agree, which perhaps is on the verge of future, very far away observations, but we should not just freely leave our fantasy. Well, I think it's perhaps enough what I could say about Kip. I mean, he's admired by many people. Yesterday, I said two things which you should, who were not there, learn. When he was celebrating 60 years birthday, so in the article about this, the author called him shaman of space and time, which probably today will be mostly revealed because he will speak about other aspects of space and time. And then I quoted Richard Isaacson, and our students certainly know Isaacson effective energy momentum tensor for high-frequency gravitational waves, where you can really localize in this high-frequency limit the density of gravitational energy. And Isaacson then left physics after this important PhD, and he became the main figure for ruling budgets for gravitational research, gravitational waves as well, but I think all general activity within the National Science Foundation. And Isaacson once said about Kip that he's our national treasure. And I said yesterday that he's not national treasure, that he's worldwide treasure, international treasure, but that today he's treasure of Kingdom of Bohemia. So please, Kip.
Thank you, Jiří, for that very kind introduction. Can you hear me in the back? It's okay. Okay, today I want to talk about geometrodynamics. That's a phrase that was coined by John Wheeler to mean the nonlinear dynamics of curved space-time, something about which Wheeler speculated in the era when I was his student and Charlie Misner was his student when we were writing our textbook. But it was speculation because we did not at the time have the techniques to solve Einstein's equations to explore geometrodynamics. So this is actually a photograph of John lecturing about geometrodynamics and other related issues. In fact, it was the 60th birthday party of Willie Fowler, who's down here in the corner, a dear friend and colleague of mine at Caltech, lecturing in Cambridge. And this was the era before transparencies. Transparencies were the era before PowerPoint. So this is going back several generations of technology. And so what John would do is he would, before the lecture, he would make all of these beautiful diagrams and words on the blackboard. And then for 1 hour, he would talk about the things that he had written on the blackboard. And so he challenged his students and his colleagues to explore geometrodynamics, to explore how curved space-time, according to Einstein's relativity, would behave in generic situations where the evolution of the curved space-time was highly dynamical and very rapid. And this then regime of nonlinear dynamics of curved space-time. Now, in that era and the years since then, we have learned a lot about nonlinear dynamics and what big roles they play in fluid turbulence in tornadoes, phase transitions in condensed matter systems, nonlinear optics, that is modern optical technology, colliding solitons and fluids, plasmas, nonlinear crystals, optical fibers, and mathematics, chaotic maps, strange attractors, and a variety of other phenomena that have been major subjects of research in other branches of physics over the last 5 decades of my own career. But it's only recently that we have been able now to see nonlinear dynamics of curved space-time. So that's what I want to talk about, because to me this is one of the most exciting areas of current research and near future research in general relativity, well, in all of physics. We had 4 decades of frustration. John Wheeler challenged us in the 1950s to explore geometrodynamics. And from 1958 to 1998, we had only analytical techniques to explore this, and we had very little progress. Wheeler foresaw this, so he encouraged his students and colleagues to develop numerical relativity, to solve Einstein's equations on computers in order to see how geometrodynamics behaves. It took nearly 4 decades of developing the techniques of numerical relativity and of improving the technology of computers, their speed, their capacity, to get to the point around 2000 or the late 1990s where you could begin to explore this on computers. And then it took 15 more years for these kinds of simulations to near maturity by about 2014. So we've only really begun to understand geometric dynamics in any depth in these last few years, since about 2014, though we learned a little bit earlier. So I wanted to give you sort of a history. Some of you who have studied relativity will know some of the early parts of this. The most recent, very few of you are probably familiar with. There are 4 arenas for geometrodynamics about which I will talk. The first is geometrodynamics near singularities in the structure of space-time, near regions where gravity is so extremely strong that general relativity fails and has to be replaced by the laws of quantum gravity, which we know, of course, very poorly. The second arena is the nonlinear self-coupling of gravitational waves, what's called critical gravitational collapse. The third arena I will talk about is computer simulations of the collisions of black holes, which create what I like to call a storm in the geometry or shape of space and time. And the fourth is gravitational wave observations of geometrodynamics from the gravitational waves produced when black holes collide. So I'll talk about these 4 arenas in which we are learning about geometrodynamics, have learned. So let me begin with geometrodynamics near singularities. And this goes actually back to Robert Oppenheimer and his student Hartland Snyder in 1939. Prior to that, Chandrasekhar and others had given strong arguments that if you had a heavy enough mass, a heavy enough star, that its gravity would be so strong that the star could not support itself against gravitational collapse, at least not after it had exhausted all its nuclear fuel. So the star would have to implode. And so Oppenheimer and Snyder explored that implosion, that collapse, by pretending the star had no pressure at all, so it was just made of dust. It was homogeneous, and they watched analytically, the collapse occur. The star shrank smaller, smaller, formed a singularity. Formed a horizon, as we now call it. They called it the Schwarzschild Singularity, but it was the horizon of the black hole, the surface of a black hole. And Oppenheimer did not have the courage or interest, it's a little hard to understand why, to ask what happened inside. All he did was got to the point where he concluded this shut itself off in the external universe. And it was for others later to explore what happened inside. And it was John Wheeler who really focused on the singularity that forms inside. Of course, Oppenheimer, Snyder, and everybody else in that era was very aware of tidal gravitational forces, that if I put my wife, who happens to be here in the audience, hang her above the black hole, that the gravitational pull on her feet is bigger than that on her head, and so she's stretched from head to foot. She's squeezed from the sides. And these are by what are called tidal gravitational forces, which will play a big role in my discussion of geometrodynamics. The same forces as produce the tides on the Earth's oceans due to the gravitational pull of the moon being stronger on the side of the ocean that's near the moon and weaker on the side away from the moon. From 1939 to the 1960s, there was great debate. Of course, there was a lot of other things going on, so physicists were mostly working in other areas. But those who thought about this had a great debate over whether singularities really do form in gravitational collapse. A singularity where general relativity would fail, where formally the analysis would say you reach infinite density and an infinitely strong gravity. So I want to give you a little bit of history, old history of singularities. In the 1960s, Lifshitz and Khalatnikov in Moscow, who were students of, colleagues of Lev Landau, they did a detailed analysis in which they concluded that no, you do not get singularities in generic situations. In fact, what would happen if I go back here is that the matter would, if there's a little bit of rotation or inhomogeneity, the matter would go in, it would swirl around and fly back out because gravity would not be strong enough to hold it and create a singularity. And they even included a proof of this in their 1960s edition, the second revised edition in English, the fourth Russian edition of the classical theory of fields in section 110, the absence of singularities in the general cosmological solution. There's a detailed mathematical claimed proof that there are no singularities, that the matter will resist forming singularities. It was a great shock then to them, to Lifshitz, who was a close friend of mine. Landau, by that time, had had an automobile accident and was more or less in a coma and never was able to really do physics again. But it was a great shock to Lifshitz when Roger Penrose in 1965 did analysis that claimed to show that in generic situations, in particular if you had an implosion, the collapse of matter to form a black hole, you would necessarily get a singularity inside the black hole. He proved this by introducing into general relativity a mathematical tool that had never been used in relativity before, the techniques of differential topology. And he showed in particular that time-like world lines would end inside a black hole. He couldn't say why. He could only prove that they would under reasonable conditions about how matter behaves. So he could not give us any information about geometrodynamics, but he could say that Lifshitz and Khalatnikov and the classical theory of fields was wrong. This caused great consternation, great unhappiness, confusion in Moscow. And this is a period where I had entered the field in 1969, so when I was going back and forth between California and Moscow nearly every year at the time. This is a picture of me, Belinsky, Khalatnikov, and Lifshitz, John Wheeler, together with Khalatnikov's wife and daughter at dinner in Khalatnikov's home in about this same era. And in 1969, Belinsky, a young colleague of Khalatnikov and Lifshitz, discovered an error in their analysis and concluded that, in fact, Roger Penrose was right, and they gave the first very approximate mathematical analysis of geometrodynamics near a general singularity. This discovery, this proof that there was an error in their analysis, it was so important to Lifshitz that they be the ones that announced it to the world. That when I was in Moscow, I think it was 1970, he gave to me a paper for Physical Review Letters announcing their error and explaining it, and asked me to hand carry it out and submit it in their behalf so it did not have to go through the Russian censors, because he didn't want any delay. He wanted them to be the ones who announced what was wrong and not have anybody else do that. And so I did, and that was immediately published in Physical Review Letters. So what was it that they discovered? They discovered, in fact, after having realized their error, that there was, that in the singularity, that there was a nonlinear dynamics of curved space-time as you approach the singularity. So here I'm showing a space-time diagram, time going up, space going horizontally. The singularity is here. It's a space-like singularity. And if I move along this world line, and my wife moves along that world line, as we get near the singularity, we lose causal contact. And so there's an actual decoupling of what's going on in adjacent world lines as you near the singularity. And so you can convert the partial differential equations of general relativity into ordinary differential equations in an approximate manner because of the spatial decoupling along adjacent world lines going into the singularity. And so that is what they did, and then they discovered that the temporal dynamics is something called mixed master, but with independent kind of mixed master behavior along these different world lines. And so, and that matter has negligible influence. So what's really going on is true geometrodynamics. It's the nonlinear curvature of space-time interacting with itself. And I want to explain this nonlinear dynamics briefly to you, for those who don't know about it, in terms of the stretching and squeezing produced by the tidal gravitational field. Now, yesterday in my lecture about gravitational waves, I talked about the stretching and squeezing produced by a gravitational wave, which is entirely transverse to the direction of propagation of the waves, a stretching of space in this direction, squeezing in that direction. This is due to tidal gravitational forces. The tidal gravitational field, EJK, is a second-rank symmetric tensor, or you can think of it as a matrix if you feel uncomfortable with tensors. And if you have two freely falling particles separated by some separation vector xi, if you take the xi as a separation vector, feed it into the matrix, or take the tensor product, inner product of xi with the tidal field tensor, throw on a minus sign, that's the relative acceleration of these two freely falling particles. So that relative acceleration, it might be a vector pointing in that direction. So the tidal tensor then describes relative accelerations between freely falling particles as a product of tidal field and separation vector. And in Newtonian theory, this tidal field is just the gradient of the Newtonian acceleration, which takes a vector, the acceleration, and you take a gradient on it, and you get a second-rank tensor or a matrix. Okay, so this is just for a little bit of background, mathematical background for those who are not familiar with this. So the tidal field is the key thing here. So the geometrodynamics near singularities, the so-called mixed master dynamics, look like this. The tidal field is a second-rank symmetric tensor. It has 3 eigenvectors and 3 eigenvalues. Those eigenvectors are orthogonal. And so those describe 3 directions, for example, up, down, north, south, east, west, whichever directions north, south, and east, west are here. And these are the principal axes of stretching and squeezing. And you have a pure stretch along one direction and pure squeezes along the other directions. And the magnitude of those stretches and squeezes are the eigenvalues of this tidal field. And in general relativity, the tidal field is the time-space piece of the Riemann tensor. Okay, so that's a little bit of mathematics. But here, so what happens is if I am here and I'm falling into the singularity, I get stretched from head to foot, or stretched from head to foot. I'm sorry. I guess I'm getting stretched from head to foot and squeezed from the sides. Then I'm squeezed from head to foot and stretched to the sides, and it's also oscillating stretch and squeeze. And so if you look here as a function of time, I'm being squeezed in the east-west direction continually, while in the up-down direction, I'm stretched, then squeezed, stretched, then squeezed. In the north-south direction, I'm squeezed, stretched, squeezed, stretched. And then an era comes to an end. Each of these things is a cycle. It's a half a period of oscillation. And then the era comes to an end, and the axes, the directions along of the stretch and squeeze, these principal axes, they rotate around to some new direction. And then you have, and this era transition is driven by the curvature of space. And then you have if you go in here, then it rotates around to a new direction. Then you have stretch, squeeze along the new direction. Then it rotates again, stretch, squeeze along the new direction. Faster and faster and faster until formally in general relativity there have been an infinite number of cycles, an infinite number of eras of stretching and squeezing described by a chaotic mathematical map. And they could write down that map. It's sometimes called a continued fraction map. So it's related to the mathematics then of a chaotic mathematical map. And this was a huge surprise. We'd never seen anything like this in general relativity, nonlinear dynamics of curved space-times. But this is what the prediction said. There was enormous skepticism in the West. By the West, I mean outside the Soviet bloc. Probably outside Moscow. But there was enormous skepticism because the Lifshitz and Kalatnikov and Belinsky were using approximation techniques. And this was an era when in the West, people like Penrose and Hawking were using very precise techniques, including differential topology, to prove very precise theorems. And there was great skepticism about any kind of an approximate analysis. Could this possibly really be right? And so this came to be called a BKL, Belinsky-Kalatnikov-Lifshitz conjecture, proved, in quotes, by heuristic arguments. So again, there was a considerable tension between the views of this in Moscow and in the West. I have to say that I was much more sympathetic to the Russians than I was to my Western colleagues, because I understood very well that there are situations where things are so complex you have to use approximate techniques. Then you do your very best to use them in a way that is reliable, and you get out what you can. And if you're clever enough, then you have a very good shot at being right, or you can even prove rigorously you're right if you work hard enough. They didn't work that hard. But there was a cultural clash, and with, as I say, Feynman were examples of people who were much more sympathetic to the Russian point of view on this. Geometry dynamics near the singularities was ultimately explored with numerical relativity. And this happened in the late 1990s and early 2000s. I won't go into it in any detail. A group of people, Beverly Berger, Vince Moncrief, David Garfinkel, Eisenberg, Weaver, and so forth. And they proved basically that the PKL nonlinear dynamics was right with a few small corrections that were hardly of any very much importance, but were interesting. That they had really gotten it very close to right by these approximation techniques. And so numerical relativity, this was the first place that it really came into play. Now there are also, it turns out, then we believe there is a generic BKL singularity inside a black hole, but there are two other singularities inside black holes, and I'm not going to tell you about them. I'm going to let you go read about them in my book, The Science of Interstellar, because they play a big role in this movie, Interstellar, and so I go into that in detail. But one of them is called mass inflation singularity, or I like to call it an infalling singularity, and the other is called an outflying singularity, or a shock singularity, proved by Donald Rolf and Amos Ori, and by Eric Poisson and Werner Israel in the 1990s and 2000. Basically, this says that there are two more singularities. They're created by stuff that falls into a black hole, generates these other two singularities. Whereas the first singularity was generated in the birth of the black hole, two more are created by stuff that falls into the black hole afterwards. And these singularities are not space-like, they're null. They're light-like. And so they're quite, again, new versions of geometrodynamics, a different kind of a singularity, different kind of behavior of warped space-time as you approach the singularity. But I don't have enough time to go into everything that we've learned. I just want to make you aware of that. And so I want to move on. Let me talk about geometrodynamics in imploding waves, a second of the four arenas in which we've been exploring geometrodynamics. This began in 1993 in an analysis of the implosion of scalar waves. I remind you that in nature, we know you have electromagnetic waves. We know you have gravitational waves. And we know it's conceivable you have a massless scalar field. We do know about a scalar field that one associated with the Higgs boson, which gives mass to particles. This requires a massless scalar field, which you can hypothesize and which is much easier to analyze mathematically than electromagnetic waves or gravitational waves. And so the first exploration of this used a hypothesized scalar field to make a scalar wave. It was a computation using numerical relativity by Matthew Choptuik, who at the time was a postdoc at the University of Texas at Austin. And what Matt did was he said, I'm going to take a shell of scalar field that is spherically symmetric. So I show it here removing one spatial dimension so it looks like it's a circular shell. And then I'm showing up the amplitude of the scalar wave. But where you see a circle here, you're to think of a sphere. And he said, I'm going to put in a very simple shape for that wave. And I'm going to adjust the amplitude, call it P of the wave. And what he found, and this was basically predictable, is if the amplitude was high enough, then there would be enough energy in this imploding wave that when it imploded and got sufficiently small, the energy would be enough that it would create a black hole around itself. And not very much wave would come back out. If the amplitude was small, it would come in, there wouldn't be enough energy to create a black hole. It would come in, there might be some nonlinear interactions, and then it would all just flow back out. And so then he asked what happened if you were right on the verge. You had an amplitude almost but not quite large enough to make a black hole, or just a little bit too much to make a black hole. What then happens? Let me explain where the nonlinearity comes in, because the scalar wave, the scalar field, is a linear scalar field in curved space-time, but it itself has energy. And so as the scalar wave implodes, the energy of that wave creates space-time curvature through the Einstein equations, and then the wave interacts with that space-time curvature. So the nonlinearity comes about through the Einstein equations. Scalar wave comes in, creates space-time curvature. That space-time curvature pulls basically on the scalar wave, and is responsible then for making the black hole or not making the black hole. And what they discovered, what Matt Choptuik discovered, was if the amplitude was a little bit bigger than some critical amplitude, the black hole will form, and the mass of the black hole is the excess amplitude, the amplitude minus the critical amplitude, raised to some power beta. And that power, he found, was 0.374. And it didn't matter what shape of wave he began with. When it imploded, it always made a black hole with mass that scaled as the amplitude minus the critical amplitude raised to this same power beta, a universal power that appeared in this formula. And if the amplitude was less than the critical amplitude, then you would not make a black hole, but the maximum curvature of space-time that would be created, curvature of space-time, radius of curvature, in relativity has the same dimensions as mass, because you multiply by g divided Newton's gravitation constant divided by the speed of light squared, universal constants, multiply the mass by that, you get something with dimensions of length. And so the radius of curvature of space-time, that radius of curvature of space-time, the maximum that was achieved before the wave, when the wave went in, interacted with itself, and then came back out, scaled in the same way with that same power. And again, it didn't matter what the original shape of the wave was, you always got that. And if the amplitude was precisely the critical amplitude, then the waves went in, they interacted with themselves in a nonlinear manner through the Einstein equations, creating space-time curvature, which then acted back on the waves. And you developed a very interesting dynamical behavior in which waves came back out with particular shapes that was repeated time and again on smaller length scale, shorter wavelengths. So it was a shape looked like that. And the next wave packet that came out was the same shape but much shorter. The next one was the same shape but much shorter. So this was discretely self-similar. All again due to nonlinear interactions. And that discretely self-similar wave shape was independent of what kind of a wave shape you send in. So I would call this organized frothing. And this is the same kind of critical behavior, it's called, that you see in phase transitions in condensed matter. As you go across some critical value of some parameter where there's a phase transition. And so here, in geometrodynamics for the first time, we were seeing critical behavior of the form of a phase transition. It's a phase transition between the phase where you make a black hole and a phase where you don't make the black hole. Critical behavior, very much like what occurs in condensed matter systems. Well, this was repeated a few years later with gravitational waves. That was much harder with gravitational waves, but much more realistic. First by Abrahams and Evans, and then by Yevgeny Sorkin in 2011. And they found precisely the same thing with the same power, beta, for the critical exponent, as we call it, 0.38. So within their accuracy, that was the same as you got with the scalar waves. And the same behavior on the other side of the phase transition. And moderately strong evidence for this same discrete self-similarity. So it appears to be independent of whether it's gravitational waves or scalar waves, independent of the shape of the initial wave. It is really the nonlinear dynamics, the geometrodynamics is behaving like what you see in condensed matter systems. You go across this phase transition. So this universality, commonality between very different kinds of physical systems, phase transition in condensed matter and vacuum geometrodynamics is really quite startling, and says there's something very deep going on here that is not at all fully understood. Since then, there have been a number of additional explorations, several different other versions of transitions across, of phase transitions have been found in numerical relativity by these techniques. But I think these explorations are still rather much in their infancy, but really very interesting in what has been found and is still being found. So now I want, for the second half of my talk, to turn to black holes and geometrodynamics in the collisions of black holes, which is more near and dear to my heart because this is something which I've worked on with younger colleagues myself. Let me begin by reminding you that black holes are not made from matter like you and I, but rather they're made from warped space or curved space and time, from curved space-time. And of course, the simple description of this is that if you have a black hole that's sitting here, and if you could go inside the black hole and measure the diameter, and you measure the circumference, the diameter will be far larger than the circumference because space is curved inside the black hole. So we like to describe this curvature in an accurate manner by taking an equatorial slice through the black hole. The black hole may be spinning, so it's described by the Kerr metric, or the Kerr solution of Einstein's equations. Take a two-dimensional surface that goes right through the equator of the black hole. And the geometry of that surface is curved. It's not flat like the top of the table here. It's curved. And so in order to visualize that curvature, we embed that two-dimensional surface in a three-dimensional space. That's not the three-dimensional space of our universe, but I think of it as a higher dimension that is outside our universe. We call it an embedding space. It's closely related to the bulk that is currently explored in what is called brain worlds physics, taking general relativity into higher dimensions. It's the fifth dimension in the movie Interstellar. So all of this shows up in some manner or another in the backstory in my movie Interstellar. So this shows you precisely what the prediction is from Einstein's equations of the Kerr solution of the Einstein's equations for the warping of space and time on the equator of a spinning black hole. So far away, this surface becomes flat, and this is the equatorial surface, but it bends down because when you get down in here, as you keep going in farther and farther, circumferences around the black hole cease to decrease very much. So you go down farther and farther, and circumferences are no longer decreasing as you approach the horizon. And so that's the depiction of the shape of space near the black hole, and this is the famous funnel that you often see in depictions of black holes. What people are not usually told is that's a funnel as seen from the bulk, as seen from a higher dimension. The color coding is the slowing of time. So this describes a piece of the 3 geometry of space. The slowing of time is described mathematically. It's describing the so-called lapse function, where the color is yellow, time is flowing at 10% of the rate that it is far away. Where it's black, time has slowed to a halt. It's not flowing at all, as seen by an observer who is hovering at the horizon and not falling in. And so the slowing of time is color-coded in this way. The horizon is at the bottom. It's a circle in the diagram, but of course it's a flattened sphere in reality, because it's flattened because of centrifugal forces, basically. So a spheroid when you restore the 3rd dimension. Then the white arrows show what's called the dragging of inertial frames, or the dragging of space into a whirling motion by the spin of the black hole. So that's an accurate depiction of the space-time geometry as predicted by general relativity. And Lisa, about which I spoke just a little bit yesterday, will extract maps of the space-time geometry of big black holes from the gravitational waves emitted by small black holes that spiral into the big black holes, and measure this and see whether this is really correct with very, very high precision, I expect, in the 2030s. Now, geometrodynamics when black holes collide. Collisions of black holes, in fact, are the most violent events in the universe, other than the Big Bang, as I discussed in my lecture yesterday. The black hole collision, during the collision, the power output is 50 times larger than the power output of all the stars in the universe put together, as I discussed. So they're very, very interesting. This is an artist diagram based on a sketch that I gave the artist in 1980, I think it was, when we were beginning to think about LIGO, and when we were targeting black hole collisions as the most likely source of gravitational waves that we would see. So we imagined in this artist depiction that black holes would go around each other, as seen from the bulk, from the higher dimension, collide and merge, and gravitational waves would come flowing off. As I have said, the power output is enormous, and no electromagnetic waves are emitted at all, except if you have an accretion disk around the binary black hole and it gets disturbed by the collision of the black holes. You may get some electromagnetic waves, but our electromagnetic astronomy colleagues have searched and not seen anything coming off from by now it's something like 15 or 16 black hole collisions that LIGO has observed. The details of the collision, that is the geometrodynamics, are encoded in the gravitational waveforms. And so this was my hypothesis, just drawing a picture without any real basis, not without much basis, of what the gravitational waveform would look like coming from a colliding black holes like this. Well, we knew that as the black holes spiraled together, the amplitude of the waves would increase and the frequency of the waves would increase. The period would decrease, the wavelength would decrease, and so you would see oscillations that got higher and higher and quicker as you see the end of that in-spiral phase here. There would be a collision, and so I just drew something that would be an interesting collision without knowing at all what it would look like in 1980. And then the final black hole after the merger would oscillate a few oscillations and the waves would die out. So that was my guess. I will return to this guess at the end of my lecture and contrast it with what it is we've actually seen. But we knew that the waveform would carry information about, details about the geometrodynamics. And so for me, this was one of the biggest motivations for LIGO, was to see the gravitational waves, and from the gravitational waves verify that what was going on was what was predicted by computer simulations, and then in the computer simulations see the geometrodynamics. So as an example, then, our first gravitational wave that we hit, that LIGO saw, GW 150914, signal came in on September 14 of 2015. The data were compared with a simulation by the SXS team that Saul Tukulski and I put together after I left day-to-day involvement with LIGO. And this SXS collaboration then, which by the time that by today, this involves a number of other institutions besides Caltech and Cornell, under Saul Tukulski's leadership. From the simulation that produced the waveform that agreed so well with the observations, the waveform that was used to extract the masses of the colliding black holes and the final mass and the final spin, that simulation, the depiction of the space-time metric, the three-dimensional geometry, well, the full space-time curvature in the orbital plane looks like this. And so here are the funnels associated with the two black holes, the color coding for the slowing of time, and arrows that are the so-called shift function, roughly speaking, showing the dragging of space into motion. Color coding shows the lapse function, the arrows the shift function, and the shape here, the two-dimensional geometry of space is seen from the bulk just before the collision. Now, this is a slide sheet, and so then for the mathematicians and theoretical physicists, I need to remark that there is a theorem that says that if you have a two-dimensional surface, a curved two-dimensional surface, you can always embed it in a three-dimensional flat space. So that's what we're doing. But that theorem says you can do it locally, not globally. And if you try to do that embedding locally, you go around one of these black holes and you come back and it doesn't match up properly. It doesn't match up smoothly. So you really can't do a diagram like this in a sensible sort of a way globally. And so what's plotted here is actually something else. This is not truly the shape of space. It's minus the sign of the scalar curvature of that two-dimensional surface divided by the square root of the scalar curvature. It's just something that was made up to resemble an embedding diagram, but something that does contain the same information as a true embedding diagram. Okay, so that's for the experts, remark for the experts. But it's then, I showed this in my lecture yesterday, it's just nice to watch the geometrodynamics. We slow the movie down as the black holes start to merge. Right at the moment their horizons touch, we stop the movie momentarily. The color coding, as I say, is the slowing of time. This is the shape of space. And then an oscillation, and the gravitational waves go flying off. So this was a true depiction of a piece of the geometrodynamics. Why just a piece? It's because it's only the equatorial, it's the orbital plane of the two black holes. Now, there's a problem that too little of the space-time geometry is depicted in this way. I want now to talk about how the full space-time geometry behaves, the geometrodynamics, when two black holes collide. Now, in order to do this, we needed a new way of depicting the geometrodynamics, something other than these embedding diagrams, something that could be used to depict what's going on in three spatial dimensions. And so this was devised by myself, by Yanbei Chen, who was my successor as the leader of this research group at Caltech, and by a number of young graduate students and postdocs who had at one time or another been in our group, and who are now spread out over Caltech, Cornell at this particular time, and NETEP in South Africa, which is where Jean-Drew Brink is. And so we published the ideas for this visualization of the Riemann curvature tensor then in Physical Review Letters a few years ago. I'm now going to get a little bit mathematical. This is for the benefit of those who know some relativity. Now, but those of you who don't, you don't need to understand this in order to understand the rest of my talk. But I want to, for those who know a little relativity, I want to say the following. The Riemann curvature tensor is the epitome, it's the embodiment of space-time curvature locally. So it is really the embodiment of what's going on in curved space-time. And it turns out that there are two pieces of this Riemann curvature tensor, the so-called tidal field, which I've already talked about, and a frame drag field. And so let me explain it this way. If we slice space-time up into space plus time, think of time going upward, and we have space horizontally, and you have some curved space, which is really three-dimensional, but I show you only two dimensions. Then when you have split space-time into space plus time, the electromagnetic field tensor splits into the electric field and the magnetic field. And we visualize those using magnetic field lines and electric field lines, and most all of you are familiar with electric and magnetic field lines. For example, the magnetic field lines around the Earth that show a dipole magnetic field. Similarly, the vacuum Riemann tensor, the Riemann tensor in vacuum, when there's no matter present or matter is not playing a significant role, which is the true here, it's actually the Weyl curvature tensor. When you split space-time into space plus time, you get a so-called electric part of the vacuum Riemann tensor and a magnetic part. Those are the phrases that have usually been used in the relativity literature in the past. The electric part is this space-time part of the vacuum Riemann tensor. The magnetic part is what is called the dual of this vacuum Riemann tensor. But these two pieces are symmetric trace-free tensors. And I talked already about the tidal field. The tidal field produces these tidal accelerations, the tidal stretch and squeeze. The frame drag field, or so-called magnetic part of the Riemann tensor, describes differential frame dragging in this sense. That if I have a gyroscope now, and think of that, this arrow as being a gyroscope, being the spin of a gyroscope. And I have a gyroscope carried by this particle P and a gyroscope carried by that particle Q, then due to this frame dragging, the gyroscope at P will precess. It will turn relative to inertial frames at Q by some angular velocity, which is proportional to the separation between those particles. And that angular velocity of precession of the gyroscope at P relative to the inertial frames at Q is the scalar product of the separation vector and this frame drag field. So BJK, the so-called magnetic part of the Riemann tensor, describes differential dragging of inertial frames in that sense. And that's the full space-time curvature tensor, the full Riemann tensor. Tidal forces that stretch and squeeze, and frame drag forces that produce differential rotation as seen by gyroscopes. Okay, now let me make this more physical. If I take Carol Lee, my wife, and I hang her above the north pole of the black hole, then she will be, if this is a fast-spinning black hole, let me hang her above the equator first. If it's a fast-spinning black hole, she will be stretched from head to foot. And you're all familiar with this. I already talked about it, due to the gravity being stronger at her feet than at her head. But if she's above the North Pole, she'll be squeezed from head to foot. And that's not well known. The tidal forces squeeze at the North Pole of a spinning black hole, a fast-spinning hole. They stretch at the equator. Almost counterintuitive. And the relative acceleration that is the amount of stretching divided by her height, is the eigenvalue, is the normal, if n is the normal vector, it's the normal component of this tidal field. And we call this the tendicity of the tidal field. I'm having problems with my laser pointer. I'm just going to pull out and change the batteries quickly. And so the stretching that she experiences at the equator, the squeezing that she experiences at the North Pole, are the magnitudes of those divided by her height then are this tendicity that comes from the phrase tendere, the Latin word tendere, which means to stretch. And that amount of stretching is then something that you can think of very physically, as I've described. And I've color-coded the horizon blue where she's squeezed and red where she's stretched. Okay. And regions where there's very strong squeezing, I call our horizon tendex, again from tendere. And where there's very strong stretching, they're colored red, and that's a stretching horizon tendex. So you have horizon tendices that squeeze. If you're above a blue part of the horizon, there's a blue tendex there that squeezes you. If you're above a red part of the horizon, there's a red tendex there that stretches you. And that's just how it is. That's what you experience if you're very near the black hole. And this is boost invariant in the sense that if Carolee falls into the black hole, she experiences precisely the same stretching or squeezing as if she's hanging there. It's quite remarkable. It's just independent of how fast she falls or whether she falls. Then above the black hole, what happens if you're outside the black hole? There are tendex lines that are the analog of electric field lines that stick out of the black hole. And these are the principal axes of stretch and squeeze. And there's a red tendex line that sticks out, and if she's above the black hole, she gets stretched along that red tendex line. There's a blue tendex line that comes out of the North Pole, swings around, goes back into the South Pole, and she is squeezed along that tendex line, stretching head to foot, squeezing from the sides. But along principal axes, these principal axes mathematically are the integral curves of the eigenvectors of the tidal field. And the amount of stretch and squeeze is an eigenvalue of the tidal field associated with these eigenvectors. So the tendicity, again, is the amount of stretch she feels, the relative acceleration of head and foot divided by her height, is that eigenvalue or that tendicity. Okay. But the key thing that I want to get at is that there are these tendex lines that stretch coming out of the equator, and tendex lines that squeeze coming out of the North Pole, but also tendex lines that squeeze and spiral around and around like this. So through every point, there are 3 tendex lines. In electromagnetism, through every point, there's 1 electric field line. Here, there are 3 tendex lines because there are 3 principal axes of stretch and squeeze. Okay. A tendex is a collection of tendex lines with very large tendicity. And so there's a tendex, very large stretching along this tendex, very large squeezing along that tendex. And I'm going to really focus on these tendices that do the stretching and squeezing as I go on through here to talk about the geometrodynamics. So in the same way, we have a horizon vorticity that Carolee experiences. If she's above the North Pole, then her head sees her feet, or a gyroscope at her feet, twisting around through differential precession in a counterclockwise direction. And her feet see her head going around or a gyroscope at her head going around in a counterclockwise direction. It's the same way if you take a towel with water in it and you wring the towel out to remove the water. If your right hand sees your left hand going counterclockwise, then your left hand will see your right hand going counterclockwise. So there's a counterclockwise twist to the towel. Here you have a tendex, or a vortex, a frame-dragging vortex sticking out of this north pole of the black hole that is counterclockwise. There's a counterclockwise twist that she experiences above the north pole, and a clockwise vortex of twisting space sticking out of the south pole of the black hole. And so then the vortex is a region with very high vorticity, a very strong twist differential precession at the south pole, and a very strong vortex, horizon vortex sticking out of the north pole, but counterclockwise. Sticking out of the black hole, there also then are the analog of magnetic field lines. These are vortex lines. They're like the vortex lines in a fluid that has vorticity in it. But these are lines that guide differential frame dragging. They guide the twisting of space. So you have a vortex of counterclockwise twisting space guided by these vortex lines. And the vortex lines are the integral curves of eigenvectors of the frame drag field. And through each point in space, there are 3 such vortex lines, because there are 3 eigenvectors, or 3 axes of the principal axes of this symmetric second-rank tensor Bij. Okay. The key thing is the vortex lines guide the whirling vortex. Now, I'm going to sort of abandon all this mathematics now that I've given those who know some relativity some sense of what underlies this. And I now want to really, well, let me just show you the vortex lines above a spinning black hole first, and then I will go in and focus just on the vortices and tendices, the regions of large twist and the regions of large stretch or squeeze. So for a fast-spinning black hole, the counterclockwise vortex lines, along which Carolee is twisted counterclockwise, they emerge from the north pole of the black hole. They go around the black hole and descend back into the north pole. And the clockwise vortex lines, they emerge from the south pole, go around, and go back into the south pole. And then there are also clockwise vortex lines that spiral around, going away from the black hole. So that's the pattern. And that diagram, together with a similar one for the tendex lines, totally embody everything there is to know about the Riemann curvature tensor, the key field that appears describing gravity in general relativity. Okay, so the key thing now is I have a counterclockwise vortex sticking out of the north pole, a clockwise vortex sticking out of the south pole, and I want to focus on those vortices. A vortex of counterclockwise twisting space sticking out of the north pole, clockwise vortex of twisting space out of the south pole. And I'm going to now watch 2 black holes collide. And I'm going to do a head-on collision, and this is from computer simulations by the SXS collaboration that Saul Tukulski and I put together. This will be a head-on collision for simplicity of 2 black holes. One has its clockwise vortex sticking up, counterclockwise vortex sticking down. This has counterclockwise up and clockwise down. I'll just remove the vortex lines and show you only the horizon vortices, and I want you to watch what happens when the black holes collide. This is a big piece of geometrodynamics, and very surprising when we first saw it in these simulations. So first thing is that you're seeing now the horizon of the black hole, the surface that if you go through that, you can't send any signals out. And initially you had 2 black holes, and each black hole had 1 red vortex of twisting space and 1 blue vortex of twisting space attached to them. Now you have a horizon that has 2 red vortices, one here and the other on the back side down there, two blue vortices, one here and another on the backside down there. So now we have, after the black hole collision, we have 4 vortices of twisting space sticking out of this black hole. And the question is now what happens? It turns out black holes, when they settle down into a final equilibrium state, they cannot have 4 vortices, they can only have 2. The Kerr metric, a Kerr black hole, has only 2. So somehow we have to get rid of at least 2 of these vortices. Since this is a head-on collision of 2 black holes with opposite spins, it seems pretty clear you're going to get rid of them all. The final black hole will not have any spin at all. It's a head-on collision. There's no orbital angular momentum. And this spin angular momentum will cancel out between those 2 black holes. So that's what you expect in the end. What actually happens? Well, let's watch. You have a blue vortex of twisting space up here. The collision occurred. Oscillation. It's now red. It's now blue. It's now red. So these vortices are fighting with each other and exchanging vorticity as they fight with each other. And that was a huge surprise to us when we saw it. So then the question is, well, what's really happening? And to answer that, we want to see what the vortices are doing outside the black hole. So here are stills that show you at particular moments of time what the vortex lines look like. So at this particular moment of time, you have this blue vortex, set of vortex lines coming out of here, so a blue vortex of clockwise twisting space. The vortex lines have reconnected. Before these vortex lines went out from the blue spot and came back into the blue spot when you only had 1 black hole. Now you have, when you had 1 black hole with 2 vortices. Now you have 1 black hole with 4 vortices. These vortex lines have reconnected, and the vortex lines come out of this blue spot, go around and in the blue spot that's back there. The red vortex lines come out of the red spot, go into the red spot that's on the back. So you're to really think that there's twisting space. There are these physical objects that are made from twisting space. They're sticking out of the black hole. They go out. And this space is twisting clockwise. It goes back in down here. And this vortex of twisting space counterclockwise goes out and comes back in down there. And these are physical objects made from twisting space-time that are attached to the black hole. Now, whenever this goes green, that means that the vortex lines are no longer attached. So they have been thrown off of the black hole. And what happens to them when they get thrown off the black hole? They embrace each other and form a ring of twisting space that starts to travel outward into interstellar space and then into intergalactic space. And with each oscillation, a new ring gets thrown off. So you have ring after ring after ring. These look like toruses. They're toruses of twisting space. Each torus is made up of a clockwise twist of space going around the torus and a counterclockwise twist of space going around the other direction around the torus. As each torus moves out through what are called the Bianchi identities, which in a freely falling reference frame look just like Maxwell's equations, the time derivative of the tidal field is the curl of the frame drag field symmetrized, because this has to be a symmetric tensor. Time derivative of the frame drag field is minus the curl of the tidal field, symmetrized. That just looks like the dynamical Maxwell equations. And so you expect the same thing. As the magnetic field moves through space, it generates an electric field. As these vortices of twisting space, which are embodied in the frame drag field B, move outward through this analog of Maxwell's equations, they generate tendencies of stretching space. And so once this torus of twisting space is broken free from the black hole, then it is forming tendencies that stretch around the torus in that direction and tendencies that squeeze around the torus in the small ring direction. And this, in fact, is a gravitational wave. A gravitational wave does not just consist of stretching and squeezing. It also consists of alongside the stretching and squeezing, but at an angle of 45 degrees to the direction of stretch and squeeze along those axes, clockwise twist and counterclockwise twist. So any local piece here is a gravitational wave that has the familiar stretch and squeeze to it, but also clockwise twist and counterclockwise twist. We don't have the technology to see the twisting yet. Maybe someday somebody, Vladimir Brzezinski, who I talked about yesterday, he invented a gravitational wave detector that in principle could see the twisting part of a gravitational wave. But the technology is not there. It doesn't begin to be good enough for this detector to really be practical. But he showed how you could actually build a detector to see that piece of the gravitational wave. Okay. So if you have an orbiting collision, it's a little different. In that case, the vortices that stick out of the black hole, as the black hole spins, after the merger, the final black hole is left spinning. These vortices that were sticking out of the horizon that are left over from the spins of the original black holes, they form a spiral pattern like spiral arms of a galaxy or like water coming off of a whirling sprinkler. And as the final black hole tumbles, these vortices then traveling outward in this trailing way generate tendencies of stretch and squeeze along with them. So this is geometrodynamics, the geometrodynamics in a black hole collision. I could go on and talk about this in a lot more detail. I don't want to. I want to just remark then, in terms of gravitational wave observations with LIGO, when we do computer simulations, then we see this geometrodynamics embodied in these vortices of twisting space, tendencies of stretching space, and we get out gravitational waveforms. And the waveforms can be quite complicated. The ones I have talked about yesterday were not very complicated, but they can be. If you have a black hole that has a spin of 60 solar masses, spinning at 91% of the maximum possible spin around this axis, a black hole of 10 solar masses spinning around with a 30% of the maximum spin around that axis. As they orbit each other, and this is the direction to Earth, you have two waveforms associated with two different polarizations, one shown in red, the other in black. And the waveforms are really quite interesting. We haven't seen anything like that as yet. We've seen much more simple waveforms. These are the waveforms we've seen in the first 6 black hole collisions. I want to emphasize, as I say, there's exquisitely accurate agreement between simulations and observation. You pick a waveform that has been seen, and you can find a simulation that will match it with exquisitely high accuracy, even in cases like this one, where the observed signal lasts for a long time, for many, many oscillations. And so we know that what we're finding in the computer simulations about geometrodynamics really is quite accurate. At least the gravitational waveforms that are emitted agree quite well. Those were the first 6 gravitational waveforms. As I said yesterday, we've now seen 15 or 16. I think it was the 16th was the one where the signal came in yesterday morning. And so we're in the business of really exploring geometrodynamics with different kinds of black hole masses and spins. But there is a question of why I was wrong when I wrote down a gravitational waveform. I said, here's what we would hope to see, and it was much more interesting during the collision than what we saw. And why have we not seen collisions with such interesting waveforms? And the answer turns out to be rather clear. The actual waveforms that have been seen, the collision part looks like that, and really not terribly interesting. And the basic reason is that the disturbances of a black hole depart very quickly. The black hole is not very good at holding on to these distortions, these departures from the chronometric. The Qs, the quality factors of the oscillations of a black hole are very, very low. And so you disturb it, and the disturbances just don't last long enough to get interesting behaviors, at least not for those parameters of black holes that we have seen. But in fact, two Caltech or former Caltech graduate students, Juan Yang and Aaron Zimmerman, together with Louis Lehner, who is a very good numerical relativist, Lehner's at either at Toronto or, no, I think he's at he's at Waterloo and the Perimeter Institute. Yeah. So based on simulations that he did and analytical work that they did, they were able to show that if you have a very fast spinning black hole, such as a spin of 0.998, which we think is probably the fastest that occurs in nature for reasons I won't go into, then the disturbances are held onto long enough that there can be a nonlinear coupling between different modes of oscillation of the black hole. But the nonlinear coupling, quite interestingly, leads to a form of turbulence, but it's a form of turbulence that is like so-called two-dimensional turbulence, in which energy cascades from small length scales to large length scales, which is opposite to the way three-dimensional turbulence behaves. And so they have analytic analyses and then also computer simulations that show this in a quite convincing way. And so I'm waiting eagerly the day when we see a black hole collision where the final black hole is spinning very fast. Then we may actually see very interesting geometrodynamics due to mode-mode coupling between modes that are held onto the black hole deep down in the throat of the black hole's curved space long enough to see turbulence in the fabric or the shape of space and time. So I want to finally summarize by saying I've talked about 4 current arenas for geometrodynamics: singularities, near singularities, imploding waves, colliding black holes, and verifying in gravitational wave observations what we see in the computer simulations of colliding black holes. But in all, I suspect we've barely scratched the surface. We have begun to understand that geometrodynamics appears to be as rich as nonlinear dynamics and other physical phenomena in other areas of physics and engineering. But when you look at the great richness that has been seen in other kinds of systems and look at how short the history is here, I think we've just barely begun to get some sense of geometrodynamics. And so I think this is a really interesting area to pursue by computer simulations coupled to analytical calculations, which are key to understanding what's going on in the simulations over the next decade or two. Thank you. I will add the remark that if I weren't now 79 and trying to pursue a career elsewhere outside of physics, since after all I did this kind of physics for the last 50 years, this is one of the areas I would be working in. But I leave it to the younger people here to pursue it while I go and try to make movies and things like that.
Well, thank you very much, Kip, for this beautiful lecture, but extremely impressive. I think it was very Wheeler-type lecture and very anti-Landau-type lecture. I told you about Kwasnica, who was working with Landau, and he had always the view that the best picture is equation. And you, of course, supplied us with a lot of beautiful pictures. Questions? So first was that in the rear, but I recognize who is that.
So yesterday you mentioned that one of the goals was to probe phenomena close to the horizon. So what needs to be done, which capabilities of the designs of the experiments need to be improved, and how do you plan to do that?
So did everybody hear the question?
I think they're occurring. I think that he's interested in happenings close to the horizon. But
yeah, so what needs to be done to improve the experiment so you can really explore things very close to the horizon, see whether the behaviors are as predicted by general relativity or whether there's some effect of so-called firewall extending out of the horizon. I think the key issue is that we need, first of all, far larger signal-to-noise ratios than we now have, and we will get that with LISA. With LIGO, the first signal we saw had a signal-to-noise ratio of 24, which is quite impressive. And I think our largest signal-to-noise ratio so far, it might be 30. I don't know for sure what it is, but it's close to that 24. As LIGO improves, as I said, we will get something like 20 times better sensitivity than now. So I think that we may get then signal-to-noise ratios as high as 500. But with LISA, in the collisions of very large black holes weighing, the optimal is probably around 1 million solar masses. We expect signal-to-noise ratios as high as 100,000 or more. And so much higher than I think we are going to get, at least in the next few decades, on the ground with these smaller black holes that LIGO sees. With these much higher signal-to-noise ratios, we can explore all variety of phenomena in the black hole mergers and in geometrodynamics far, far better than we can at the present time. I think the other key thing is we'll begin to build up some understanding of what kind of a system is best in terms of the masses and spins of the initial black holes in order to really probe what's going on in the space-time geometry near the horizon. We don't have that understanding now. I think the understanding will come primarily from computer simulations, and it's going to take a lot of exploration of with computer simulations to get some sense of that, so you know where it is you're most likely to be able to get the information that we want to get.
Okay, another question. Okay.
I'm wondering if, since gravity waves have shown to be somewhat similar to light waves, as they propagate around a mass, just like light slows down and refracts through transparent materials, might you expect gravity waves to exhibit similar behavior when they interact with a mass? Would you see interference patterns downstream from a mass? Would you see things like wrapping around or reflecting off of a mass when gravitational waves encounter matter?
So the key to this is the geometric optics regime. That's the regime where the wavelength of the waves is small compared to other length scales present in the problem. So where the wavelength of the waves is small, if you're talking about waves near a black hole, the wavelength of the waves is small compared to the size of the black hole. The wavelength of the waves is small compared to the radius of curvature of the wave fronts. Then you can build an approximate solution to Einstein's equations for the propagation of the waves based on the idea of rays along which the waves propagate. And you can then do what's called a two-length scale expansion of the Einstein equations in the ratio of the wavelength of the waves to this larger length scales that are present. This is what Richard Isaacson did that Yishi referred to, this man who really was the key person in Washington, D.C. that made LIGO happen and that created in the U.S. The modern era of relativity research. His PhD thesis with Charlie Misner was developing that. And when you develop that, it turns out, not surprising, that the rays along which the gravitational waves propagate are null geodesics, identical to the rays along which an electromagnetic wave propagates. It turns out that the amplitudes and frequency of the waves evolve in the same way as those of electromagnetic waves. So you get the same gravitational deflection of the rays along which you propagate. You get the same Doppler shifts. You get the same gravitational redshifts. You get the same cosmological redshifts. You get all the same phenomena when, in terms of the interaction of these waves with this curvature of space-time cosmologically are those of massive bodies. The places where there are differences are when nonlinear effects come into play. Electromagnetism is linear, and gravitational gravity is nonlinear. And so you see, but that's not the short wavelength limit. And so in this short wavelength limit, everything is the same, basically, as for electromagnetic waves.
Okay, this lady there was, this is Anna.
Yeah.
Good. So Anna.
Okay, thanks for the very good talk, the first thing. And my question is, when you mentioned that there are 3 singularities, 2 of them located in the horizon and one the inner BKL1, so if some matter is falling to that black hole, is it possible that some matter pass the first 2 singularities and reach the inner one, or not? So
we don't know. But let me explain what these other 2 singularities are about. I didn't want to take the time, but maybe it's worthwhile if I do this. So the BK, well, let me also say, we're not 100% sure of what I told you about the 3 singularities, because thus far we only have approximation techniques that have been used to analyze this. And to be absolutely sure that the picture I'm going to tell you is correct, we really need computer simulations. And the groups that have been working on numerical relativity, they've been working so hard to produce gravitational waveforms for LIGO data analysis that they have not yet done very much with the interiors of black holes. But again, if I were working in that field at this point, that's something I would do now, and let other people do the LIGO stuff. I would be trying to explore the interior of a black hole. But based on the approximate analyses, this is the story. And I describe it physically in my popular book, The Science of Interstellar. So if you fall into the black hole, then time is so slowed inside there compared to far away that everything that falls into the black hole after you, over the future billions of years, you see descending on you in a fraction of a second, in a sort of shock wave. And that is this so-called mass inflation singularity. And so you have what may be a huge amount of stuff that is falling onto you, and its gravitational field, the gravity associated with that. And so that's not a very pleasant singularity, but it's different from the BKL. It doesn't oscillate in a chaotic manner. It's simply, what gravity does is it has a profoundly fast squeeze along 2 directions and stretch along the 3rd direction. And it turns out when you analyze it in detail, again using approximate techniques, this is work of Werner Israel, originally Werner Israel and Eric Poisson, and then others have explored it in greater depth. Turns out that the total amount of stretch that you experience before you hit the singularity and Einstein's equations fail is finite. So the rate of stretch is infinite, but it happens so fast that the total amount of stretch is finite. Another way to say it is that the double time integral of the Riemann tensor is finite, even though the Riemann tensor is diverging. And so we don't know what happens after that. You're not yet dead, maybe. But you've hit the point where the laws of quantum gravity take over, and at least where we don't know how to compute what happens after that using Einstein's equations. The other singularity, you have fallen into the black hole, and everything that fell into the black hole in the past, some small amount of it has scattered back up toward you, scattering off the curvature of space-time of the black hole itself. And that, again, as seen by you, comes up in a thin sheet that you see is lasting just a fraction of a second, a gravitational shock wave. And that's probably, in some sense, the least lethal of 3 singularities. That's the singularity that Cooper falls into in the movie Interstellar and survives somehow. But again, it's a finite, total stretch and squeeze. And he has the good fortune that he is caught by a vehicle called a tesseract that was built by beings that live in the fifth dimension, and he's carried up into the fifth dimension and out of harm's way. But that's a speculation that I don't take terribly seriously, but I can't disprove it, and so that's what we used in the movie.
Well, if I may say, you indicated that this singularity, which is actually in the inner Cauchy horizon, it's now. I think that people hope that it will be space-like eventually, that conjecture was such that it will be. So
yeah, again, I think we don't have, we need numerical relativity simulations to know for sure, but the upflying singularity is at what is called the inner Cauchy horizon. The infalling singularity is at what is called the outer Cauchy horizon. And they both are null in perturbation theory before you take into account stronger nonlinearities. But future research may show, as you say, that becomes space-like. Or it may join on to the BKL singularity when you get down deep enough.
Okay, I know this is gentleman. So please,
I have also a speculative. Thank you. I have also a speculative question. Under present physics, we know that we can't save anything that crosses the event horizon except as Hawking radiation coming back. But hypothetically, what if we could move the horizon, the event horizon itself? Like, I mean, if the weak energy condition could be violated and traversable wormholes could be built, if we could make one and throw one mouse into the black hole to reach falling observer or anything before they hit any singularity.
So there are technical papers have been written about this by Igor Novikov and colleagues. And I think it's very interesting. I'm skeptical that this, well, first of all, I'm skeptical that wormholes actually can, if they can be formed, I'm skeptical that they can be held open long enough that you can travel through them. But we don't know. We don't know. And so there are very interesting speculations, such as you described, that have been analyzed under various assumptions about how the laws of physics behave in regimes where we don't really understand it. And you asked me, what if? I'm not the expert. Go ask Igor Novikov or one of his collaborators. Yeah.
Did you ever look into visualizations of geometrodynamics in the mathematically equivalent formulations of GR, like the teleparallel or other such mathematical reformulations that don't even have curvature?
So people can't hear you.
So the question was if you ever did any visualization in the mathematically equivalent formulation of GR, like the teleparallel one that doesn't even have curvature, and what these kind of scenarios would look like.
So people are just beginning to explore numerical relativity and other variants of the theory of gravity beyond the Einstein version. And in particular, the Saul-Tucholsky's collaboration, the Caltech Cornell, now includes the Albert Einstein Institute and others. They are doing this, but there's not very much in the way of results as yet. But it is something that is beginning to be explored.
Okay, so this gentleman was, so for your neighbor and then for others, okay? Sorry, I forgot your first name.
Well, I have a provocative question. Do we know anything what happens with quantum fluctuations close to BKL regime?
I'm sorry, I didn't.
If we consider quantum fluctuations of different fields, including quantum fluctuations of geometry, let's say quantum fluctuations of gravitons, what will happen with them in McMaster or BKL singularity or close by before the curvature is big?
I don't know. I mean, I think this is an interesting kind of question, but I've not followed the literature in that area in recent years, so maybe somebody else here.
Yeah, maybe Lars Andersson, who is here, but he would consider it classically probably. This is our actually new group, Russian Greek group of cosmology in Physical Institute. But I have one recollection, very nice recollection, in the time when I could not travel elsewhere, only to Moscow. So whenever Lifshitz would speak about it, so Zeldovich at the end of the lecture would put his hand up and said, and how many oscillations can it be done before Planck regime is, and he would say 2, 3, he always wanted, he asked the same question whenever Lifshitz would speak. Yes?
Who remembers the answer?
Sorry?
Who remembers the answer?
Well, I'm slightly older than you.
Well, I mean, the answer is more than 2 or 3. I think it's more like 20 or so. It's several tens of oscillations, but it's not very many because the time scales to which you evolve are reduced so rapidly. But nevertheless, I think in terms of understanding the structure of general relativity, I think it's well worth exploring the entire mathematical evolution to give us a handle on geometrodynamics as a separate issue from the issue of now what does quantum gravity do after maybe 20 oscillations. But clearly what quantum gravity does after 20 oscillations is a much more fundamental issue, but it's not an issue that I think we're prepared to answer today, whereas we can answer the question of what is the entire pattern of a BKL evolution.
So if we will have a LISA detector and we can be able to observe the region near to horizon, do you think that we will see firewalls or we will see just a regular empty space there?
So I will comment on firewalls, okay? I have a different view from most of my colleagues. And so I preface this by saying that this is not the view that, I don't know how many, if any, of my colleagues would support my viewpoint, but it's the following. That I find firewalls so strange that I am quite prepared to, and find quite attractive, the idea that information is lost. And I see an attractive way that this occurs if the most fundamental formulation of quantum theory is Feynman's path integral formulation. Then that is readily adapted to loss of information, readily adapted to non-unitary evolution. And the simple way in which this happens is in Feynman's formulation, you compute probability amplitudes to go from this initial state to this final state by summing over histories. Wheeler has long speculated long ago, that in that sum over histories you should include changes of topology, and I would argue in the same spirit you should also include finite probabilities for histories that have closed time-like curves. The moment you put in a history that has closed time-like curves, you lose unitarity. But you can still analyze the evolution and compute a probability amplitude to go from here to there in the presence of closed time-like curves and non-unitary evolution by using, for example, the Hartle-Gell-Mann variant of Feynman sum over histories, their generalized quantum mechanics. And that is readily capable of dealing with these kinds of things. And that kind of formulation, in the absence of closed time-like curves, you just get ordinary quantum mechanics, but in their presence you get a capability of dealing with things like loss of information down black holes, loss of information that is tied into there being finite probability amplitudes for in the sum over histories, for histories where there are closed time-like curves in the, say, in the vicinity or in the interior of the black hole.
So to summarize, you think firewalls do not need to exist?
if I'm right, that the Feynman approach, as for example generalized by Hartle and Gelman, if that's correct, then you don't need firewalls, you don't need any of the struggles that that today's very best theoretical physicists are going through to deal with information loss. You just don't need it. But you have to open yourself up to conceding that, or speculating that the standard Hamiltonian formulation of quantum mechanics is not the ultimate correct formulation, that it is some variant of Feynman's, some of our histories. So anyways, I say that's my minority point of view.
Well, Nikolai is very skeptical also. He says so clever people are arguing about these things, but they don't really understand the physics combination. Sorry, could you remind me, Kostas, are you? Yes. Oh, good. So this is cosmologist Kostas Korris. So please, Kostas.
So in the study you showed about this collapse of the scalar field from Choptuik, which was really fascinating. So, so emergence of critical behavior, which is very similar to condensed matter systems.
I'm lost. Can you start over again?
Yeah, so the emergence of critical behavior in the Choptuik simulations of scalar field collapses.
Yeah.
It's really striking. And I was wondering, in the case of condensed matter systems, when you have this critical behavior, it has been analyzed, it's been quite a recent field of research using conformal field theory because of the emergence of approximate conformal symmetry at the critical point. So I was wondering whether something similar has been done in GR. Or
I don't know. I've not followed the work on critical behavior in recent years, so somebody else here in this room may know. I'm not very up to date on this. There has been a fair amount of effort in this area that I just haven't followed.
Yeah. Somebody knows, but they are too shy. Or they want to keep it secret. So, questions? You already asked questions, so here, yes.
Are there any plans or ideas to measure the twisting of space directly?
Yeah. So, here's the mic.
Okay. Are there any ideas or plans how to measure the twisting of space directly? And is it worse to measure it separately from squeezing and...
So there are no plans to measure the twisting of space in a gravitational wave. Because the technology, at least for the one design, conceptual design for such a detector that I know about is Brzezinski from, it has to be the late 1960s, a very long time ago. Measuring then, in this case you have to measure differential motions, which you cannot do with anything like the accuracy you can in looking at differential displacement. So a differential twist is much, much harder to measure than using interferometry for differential displacements. And so I don't know of anybody who has thought seriously about trying to do that in a gravitational wave. Now, in some sense, the frame dragging experiments done by gravity probe B to measure frame dragging by the spin of the Earth, done by Ciuffolini's satellite, Everett, gravity probe B, which is Francis Everett, then Ciuffolini and his Lagios experiments, which also, I think, see believably this frame dragging. They are measuring just this differential rotation. They're measuring the angular velocity of turning of space near the surface of the Earth compared to higher altitude, where far from the Earth, where the inertial frames are tied to the distant stars. So they're seeing that twist of space around the Earth, not with very good precision, but they see it.
Yeah, that was unfortunate. It lasted very long before.
Yeah, that's right. But the other place where we're seeing it, and we could well have some interesting accuracy is in now the measurements that are being made of the shadows of black holes. There's this recent observation by the Event Horizon Telescope collaboration that I think you have probably all seen of the image of the black hole in the galaxy M87. In that image, you see the bright spot caused by gas that is moving towards you around the black hole, and the dimmer on the other side. So you know where that spin, and that gas is dragged into motion by the spin of the black hole. So you basically are seeing the spin of the black hole. You also have, in other observations, you have measurements of the jet that is shooting out of the black hole. And deep in the technical paper, I think it's paper 4 of the series of papers that the Event Horizon Telescope team published about a month ago, they have a brief discussion of the relative locations around the black hole of the jet where it appears to be sticking out, and of the frame dragging, basically the equator of the black hole associated with frame dragging. And they argue, though I have not spent the time to really understand the details of the argument, that from these combined observations of the jet and of the frame dragging seen by the bright spot around the black hole shadow, that what is really going on is that the jet is powered by the so-called Blandford's-Nyack process, which is a process where you have a magnetic field that is sticking through the black hole. It's held on by accreting gas. And the magnetic field is dragged by this differential frame dragging. It's precisely the same phenomenon, the twist of space, dragging fast near the horizon, more slowly farther away. And that differential frame dragging is generating the electric fields that power the jets. They are, and so there are magnetohydrodynamical simulations of this process that are the best simulations that have been done. The process was discovered by Blandford and Nyack in 1976. The best MHD simulations give then a direction for the jet and a direction for the equator associated with spin dragging that's in accord with what is seen observationally. And so they argue that this is very strong evidence that what is going on in powering the jets is the twist of space. It is the frame drag vortex interacting with magnetic fields. These data are going to get stronger and stronger, better and more interesting, as in this collaboration they go to shorter and shorter radio wavelengths. They're now operating at, I think it's 1.8 millimeters or 1.3 millimeters, I forget. But they will be able to go to shorter and shorter wavelengths and be able to build up much better observations of what's going on with the gas and the magnetic fields near in the vicinity of the horizon of the black hole in M87, and also the black hole in the center of our own galaxy. And I think there's a very good possibility then that we will get really nice studies of vortices of twisting space coming out of this, combined with the observations of the jets over the next decade or so.
Your question reminds me how progress was made, namely people who did observe gravity B, the dragging of gyroscope. So they claim that they have to have such angular resolution that they can observe a dog on the moon. They didn't say what type of dog, but still it was dog. But the people who do this shadow, they can observe a little coin on the moon. So you see how the resolution becomes more and more precise. So are there other questions? Okay, Michal Křížek. You had questions yesterday, so short question.
Yeah, the analytical or exact solution of Einstein equations for the colliding black holes is not known. So are there any guaranteed error estimates of the numerical error?
Yes, so the key to this is that the SXS team, Tucholsky's team, Cornell, Caltech, and now other institutions, insisted in the era when there was great difficulty doing successful simulations, they insisted on reformulating the Einstein equations in a manner where the evolution equations are strongly hyperbolic. And they succeeded in doing this. Doing that successfully caused them to be slower in getting mature simulations than other groups who didn't insist on that. But having insisted on that, you have theorems about convergence, for example. And so they then check in their simulations that all the theorems about how convergence should behave are satisfied by their simulations. So they do simulations with the equivalent of grid size, which is really number. They're using pseudospectral methods, so they expand in a set of basis functions. And so as they go to a larger and larger number of basis functions, which is equivalent to finer and finer grid, they watch how the convergence occurs, and it occurs in just the way that the theorems say it should. And so they have a very high confidence that what they're seeing is the truth at the level of that is dictated by these convergence theorems.
I would be interested in knowing your opinion on effort of people who try to solve cosmological phenomena using the condensed matter analogies. For example, the work of Grisha Volovic, and there are certain analogies like, say, Kibble-Jurek mechanism of existence of quantized vortices and so on. What do you think about this line of scientific inquiry?
I don't know enough about it to comment. I have not followed this, so I really can't comment. Maybe other people can, but yeah.
You want to comment? But let me ask you, you believe in, it's an unscientific term, believe, but in dark energy. I am saying to students that gravity may be described by two constants, and cosmological constant is still okay. And we also don't understand the origin of gravitational constant, is it? No. So,
yeah. So when the evidence for the acceleration of the universe was first presented by two supernova teams, I didn't believe it. And I didn't believe it because supernova observations have a long history of the observers underestimating their systematic errors, the history going back decades. Then the evidence came in from the CMB observations saying the same thing. And you also had pretty strong evidence of something like this in the disparities between the ages of the oldest stars and the Hubble expansion rate. And so with those three pieces of observational data, I threw in the towel, and as did, I think, all other colleagues of mine who were skeptical. And I think that the universe is accelerating. There is something like dark energy going on. But I was very, very skeptical. I find it rather unpleasant. But it's very exciting. Then the question is it really just a cosmological constant that is perhaps associated, as it may have been Sakharov first argued, I'm not sure, or Zeldovich, associated with the renormalized stress energy tensor associated with vacuum fluctuations, where we don't know how to do the renormalization, but the observations are telling us. Or is it something else? And so my own personal guess and hope is that it's something else. That would be much more interesting, and I love it when things turn out to be much more interesting, but I have no wisdom about it.
If you allow me, Kip, I will do one correction only.
Yes.
Okay. It's not Hubble expansion, it's Hubble-Lemaitre expansion.
Yes, Hubble-Lemaitre, yes, yes.
You know, this
I think it's officially that now. The International Astronomical Union has declared, I think that's right.
Okay, I think that the leadership of faculty who enormously appreciates your presence, etc., knows that there is still program. We have to finish. If you are interested and you can ask more questions, there is tomorrow lecture at 5 o'clock, and the room should encompass 550 people at the Faculty of Law. So please come there. And if you are having questions, say, I was there yesterday and I was not able to get the answer, and I will pick you up.
Thank you.
Well, thank you, everybody. I thanked already you, the audience, for coming. I thanked Jiří Bičák for bringing this wonderful guest, but I didn't thank to Kip yet. So, yes. Kip, thank you very much for a wonderful lecture. And on behalf of the advisory board of the Dean of the Faculty, who approved giving you the gold commemorative medal of the faculty, I will just read 1 or 2 lines. The letter is much longer. The medal is presented in acknowledgement of your most outstanding achievements in many areas of general relativity and gravitation and their applications in astrophysics and cosmology. We also highly appreciate your role as an educator of many influential scientists all over the world and your wonderful achievements in science popularization. And there is more and more, but the medal will be actually given to you by Vladimír Baumruck, the Vice Dean for Physics.
Thank you very, very much. It's a great surprise. Thank you. Wow. Thank you. Thank you so very much. Thank you.
And with the medal, there should also go a bottle, but don't expect a bottle of wine. At the grounds of the Faculty of Mathematics and Physics, you get a 4-dimensional one.
Wow. I've never had such a thing. Thank you.
It is possible to fill it by liquid, but this is a puzzle for you.
Oh, it is possible?
It is possible.
Okay. I'll let you put it back in. You know how it should go.
Thank you again.
Thank you. Thank you very, very much.